Let's get started. So we're working on chapter 6. And the way we have, let me just share here. Share screen. Okay, as far as the syllabus is concerned, I was just looking at it. I don't know why it's so giant. So as far as the syllabus is concerned, we had last week working on chapter 6. This week is for all chapter 6. But I'm going to try and get some of chapter 7 into chapters this week here. So because next week, and I'll send an email out, I'm going to cancel class on Wednesday morning at 8 a.m. Because it will be like right after the election. And I don't know for you, but that's like New Year's for me. So there will be tears shed either way. And you guys don't need to see that from me. So we will not be meeting on Wednesday of next week. Okay. But in order to do that, we got to push lecture a little bit this week. So let's go ahead and just get started. So we got through most of this chapter and we left off here. Yeah. So we had worked on, if I gave you the chemical formula, you could calculate the mass percent. So if I was to give you something like CaCl2, and I wanted to know what's the chlorine's percent, okay? You would take the mass of chlorine times 2. Divided by the mass of the whole compound times 100. All right, so you figure out the percentage of whatever the part was. Pretty straightforward, pretty easy. Can we go the other direction? And the answer is yes. I can give you the mass percent. So I could say, hey, this thing is 58% chlorine and the remaining part is calcium. What's its chemical formula? And you would be able to go to a chemical formula. This is going to take a little bit more work though. So just to do a backstory on going from here to here. So an empirical formula gives us, remember, an empirical formula gives us the whole, the smallest whole number ratio of each type of atom in our compound. So like hydrogen peroxide, this thing down here would be its empirical formula. So it's 1H for every 1O. But that's not what it actually looks like. The molecular formula is always going to be a whole number multiplier of an empirical formula. The molecular formula is what is actually happening if we were to look at it on an atomic level. So it's actually 2 hydrogens combining with 2 oxygens. But if I was to reduce this down, I would get my empirical formula. So the molecular formula is whatever your empirical formula is times some value n, and n is just an integer. So n would be 1, 2, 3, 4. It obviously isn't going to be a decimal value, so it wouldn't be 1.33. In this case, to get from the empirical formula of hydrogen peroxide to the actual molecular formula, I'd multiply it by a factor of 2, or n equals 2. Let me give you one of these. So if I have C11H22O33, this is the molecular. I want you to write an empirical for this. And I want you to tell me what the N value is. So remember, the empirical is just the lowest ratio of whatever your molecular is. And then the N value is how you would get from one to the other. So what I'd have to multiply my empirical by. So hopefully you can see that each of these values is divisible by 11, right? So 11, 11, and 11. So my empirical formula for this thing, or the lowest ratio of this really clunky molecule in real space, this is what the molecule looks like. It's real clunky and big. But if I just wanted to reduce it down to what the ratio is, the lowest ratio would be CH2O3. And for every carbon, there's 2 hydrogens and 3 oxygens. Now in real space, it's really 11 carbons bonded to 22 hydrogens and 33 oxygens. My N value for this case would be 11, right? Because in order to get from here to back to here, I multiply by my N, which is 11. So why are we talking about that? Well, that comes into play when we do some of these problems. Okay, so let's talk about the decomposition of water. So you know the formula for water. I trust that you know the formula for water, but we're going to prove the formula for water. So let's say that we decompose a sample of water into oxygen gas and hydrogen gas. And when we separate it out, we get 3 grams of hydrogen gas and 24 grams of oxygen. How can we determine its empirical formula? So go ahead and write that down somewhere on a sheet of paper that we have 3 grams of hydrogen and 24 grams of oxygen. So let's say you didn't know what the formula for water was, but you were given these values. Could you come up with a formula? We could come up with at least an empirical formula, its lowest ratio. So the first thing we want to do, where are those slides? There, okay. I'm going to go through the rules. So the first thing you want to do is write down or calculate is given the masses of each element. So in this case, we were given the masses, right? We were given 3 and 24. This is important. If your sample has to happens to be given as a percent composition, so instead of saying 3 grams, it said 3%. I want you to just assume that it's a 100-gram sample, and you can take that percentage number and you can just cross it off and exchange it for a gram. All right, the next thing we want to do is convert each of the masses into moles. How do we do that? We use the molar mass. Why do we need to convert mass to mole? Because an empirical formula, or these chemical formulas that you are writing, are talking about the relationship between atoms, not masses. Or they're talking about the relationship between moles of each thing, not mass of each thing, not grams of each thing. So a formula is a molar relationship, not a mass relationship. So sometimes what people will do in these problems is they leave them in mass and they forget this step. Always step 1, convert to moles. Then we're going to write down a pseudo formula where we use these kind of clunky decimals that we got for our mole values, divide by the subscript, that's the smallest, and then multiply if we need to. Okay, so those are the steps. Write down in grams. If it's percent, change it to grams, convert to moles, write down a pseudo formula with the mole value as its subscript, divide by the smallest subscript, multiply by a factor if we need to get it to a whole number. So we're going to do that for this. So the first thing we need to do is convert from grams into moles. So in order to do that, I know that 1 mole of hydrogen is equal to 1.01 grams of hydrogen. Oxygen, for every 1 mole of oxygen, it weighs 16 grams of oxygen. So we get into our mole values. In this case, we have let's see. So this first one is roughly 2.97. People say, how many decimals? Take as many decimals as you can. This one over here, we've got 24 divided by 16. This gives us 1.5. Okay. So the steps say to write a pseudo formula. You don't have to, you could just divide here if you want to, but I'm gonna write a pseudo formula. So I'm going to take these values that I've gotten, because what we've done now is we've created a mole relationship. So this is how many moles, it's almost 3. This is how many moles of hydrogen there are. This is how many moles of oxygen there are. That is the correct ratio of those two things. The unfortunate thing is that they are not whole numbers. So I'm going to write it out, hydrogen, and I'm going to put that as its subscript, 2.97. Oxygen, I'm going to put this as its subscript, 1.5. Now, I want to get these into whole numbers. So the fastest way to do that is to find whichever one is the smaller decimal. In this case, it's this 1.5, and divide both numbers by that. So I'm going to divide this by 1.5, and I'm going to divide this by 1.5. That anything divided by itself becomes 1. So I have 1 oxygen. 2.97 divided by 1.5 is close enough to being 2. H2O. And we're done. Okay, so we've now been able to derive our formula from a mass value. We take the mass, convert it to moles, get our moles, write a pseudo formula with those clunky decimals, divide by the smallest decimal. Hope you get whole numbers. If for some reason you didn't get a whole number here, then you want to multiply by some sort of factor. Let's see the values here. Here are the factors. So let's say if you ended up with 0.5 still left over, you'd want to multiply it by a factor of 2, everything by a factor of 2 to get rid of that half, half decimal. If it was 0.25, you'd multiply it by 4. If it was 0.33, you'd multiply by 3. Hopefully some of those are kind of common sense. Would it be okay to round up to 3 with a whole number as 2.9? So yeah, I mean, it's close enough. I like to leave my rounding until the end, Suzanne, until the last step. So if I'm getting something that's decimaled here, I like to preserve it until the very end. Because sometimes those decimals can make a little bit of a difference. So hold on one second. My French bulldog does not want to be in here right now. So let's do a couple of these. We'll play around with some of the numbers and see if we can come up with something that maybe gets us into trouble by rounding too early or so on and so on and so on. We don't want that. Okay, I don't really like the slides a whole bunch. I've got a couple practice sheets on this. I'll use some off of that. No, I don't want to do this one. There you go. Okay. So this worksheet has a bunch of practice with what we've been doing or what this is, and it also has the answers so you can like go through them on your own and check. Let's do this first one though. It says, what's the empirical formula for a molecule containing 65.5% carbon, 5.5% hydrogen, and 29% oxygen? So write those values down because I'm going to do it on a different sheet here. Let's minimize this. See. Okay. Hold on. Never understood when people had like 2 computer screens. You know, they always had like these multi-screen setups. I'm like, oh, come on, you're not that important. And now that I'm doing this, I really want to have 2 or 3 screens because there's just not enough room on this little laptop screen for me. All right. So our values were 65.5% carbon, 5.5% hydrogen, and 29% oxygen. So when we were talking about those steps, I had said the first thing was that if you happen to get percentage values, you can assume that you have a 100-gram sample. So that's what we're going to do. We're going to assume we have 100 grams, and I can take these percentages and right off the bat, just convert them into grams. Okay, so I'm going to get rid of the percentage and I'm going to convert it to gram. Because if we have a 100-gram sample, that's how many grams we would have of each. Now we've got to get out of grams and get into moles. So in order to do that, 1 mole of carbon is 12.01 grams of carbon. 1 mole of hydrogen is 1.01 grams of hydrogen, and 1 mole of oxygen is 16 grams of oxygen. What I get a lot of times is people writing a formula using these values. Remember, it's not a mass relationship. It isn't a gram relationship. Our formula has to be written in a relationship of moles. So that first value, 65.5, we divide it by the 12.01, and we end up with 5.45. This next thing, 5.5 divided by 1.01, 5. Ooh, I like this, 5.45. 2 5.45s, I like that. Okay, that's like a 1-to-1 ratio. Let's see what this last thing pops out. 29 divided by 16 gives us this other random number, 1.812, something like that, 3. So these are actually how many moles of each thing are in my formula. They're a correct ratio. They're just not whole numbers. So we need to get them into whole numbers. So we can write a pseudo formula for this thing. So I have carbon, and right now it's going to have a subscript of 5.45, which I know seems funky. We're going to get rid of it in a second. The decimal part, 5.45. And then oxygen has the base 1.813. Now the rule here, after we've written the pseudo formula, is that we divide by the smallest decimal. So of these things, the smallest decimal is going to be the thing that's attached to the oxygen. Okay, so I'm going to divide everything by 1.813, not just the oxygen. I divide all of them. 5.45 divided by 1.813 gives me 3.006. That is close enough to 3 to be 3, okay? So if I take this number and I divide it by this number, I get 3.006. We're gonna go with 3 for that. If you get a number like this, 3.252, that is not close enough to 3 to round. We don't round that. All right. Hydrogen, we also get a value of 3. Oxygen gives us obviously 1. Anything divided by itself is 1. So we don't even need to write anything there. So there is our empirical formula. You have to follow the steps specifically. You don't get creative on how you do these. Just follow the steps. So I'm going to have you work on one on your own. Let's go back to that worksheet. That worksheet, that's a good worksheet. I like this worksheet. We'll skip 2 for right now on this sheet and we'll come back to that. I want you to do number 3, okay? So it says, what's the empirical formula of a molecule containing, we've got 18.7% lithium, 16.3% carbon, and 65% oxygen. And so I want you to go through that step by step and come up with an empirical formula. And when they say empirical, they just mean the lowest ratio. We'll get into molecular in a minute. So 18.7% lithium, 16.3% carbon, and 65% oxygen. I can zoom in a little bit here. And I'll give you all, it's 8:26. I'll give you 4 minutes to work on that. So you have till 8:30. So when working with this one, there are certain things in chemistry that I like really enjoy doing. I find very satisfying. Naming is one of them. Stoichiometry, which we'll get into a little bit later, is one of them. This is also one of them. I don't know why. I find this really gratifying though, when you can actually get to the correct formula. So we've got our percentages. So first thing I'm going to do is say, hey, I've got a 100-gram sample. I can ditch the percentages and I can say that those are in fact grams. So gram, gram, whoa, gram, gram. We need to convert these all into moles. So 1 mole of lithium, what, 6.941 grams lithium. 1 mole of carbon, 12.01 grams of carbon, and then oxygen is giving us that 16 grams of oxygen. So let's see what we pop out here for our values. Again, don't be freaked out if the numbers that come out for your moles are really like sticky. They're like really decimaled, because when we divide by that smallest number, it usually takes care of itself. I got 2.69 here, 16.3 divided by that 12.01, 1.36. If your numbers are slightly off, like you're at 1.37, that's okay. The 65 divided by our 16 gives us 4.06, something like that. All right, so we're going to write our pseudo formula. I'm gonna do it down here, 2.69 is the first thing. So I've got lithium with 2.69. I've got carbon with 1.36, and I've got oxygen with 4.06. So I divide everything by whatever my smallest decimal is. That happens to be this thing here. So I'm going to divide it by that, 1.36. Lithium, we get 2.69 divided by the 1.36. We get 2. I got 1.977. That's close enough to 2. Anything divided by itself is 1. And then 4.06 divided by the 1.36 gives us 3. Li2O3. Oh, it's lithium carbonate. Is that system making sense? Don't get creative. Just go through the set of systems, or the system set, you know, if you need to, again, because lecturing and stuff is a little bit different. You can even, you may find that it's helpful to have this flow chart. I want to do one where we end up with a decimal, but I'm not seeing one. See if I can find something here. Let's do, I really want to make sure it's one that has a decimal. Hold on one second. Give me 1 minute. I'm going to work this one problem out just to see if it does what I want it to do. one doesn't do what I wanted to do. Oh, come on. Okay, let me look at that other formula sheet in a second. I'll be able to. So. Yeah. Okay, let's do. Yeah, I like that one. Okay, number 3. All right, we're gonna do number 3 here. This will get us into that squirrely situation if after you divide, you still don't have a whole number, that you have to use a multiplier. So number 3 says we have a 170 gram sample of an unidentified compound. So we don't know the formula. It's 29.84 grams sodium. It's 67.49 grams of chromium, and it's 72.67 grams of oxygen. What is the compound's empirical formula? So you go ahead and work on that for 4 minutes, and then we'll reconvene. I'm going to write it over here on right, so there are the values. 29.84 grams of sodium, 67.49 grams of chromium, and 72.76 grams of oxygen. Okay, so working with, oh, comment here. When you're putting the mass for the compound, how many decimal places do you do? Lyric, you use as many as you can. I would say at least 2. That's why you see like something with oxygen, because it's 15.99994. I just round it to 16 because 2 decimals will still round it up to 16. 2, 3, something like that. All right, so for sodium, we've got 1 mole of sodium is 22.99 grams. Chromium is 51.996. I'm gonna go with 3 on that one, chromium. And then this one's a little bit smushed up here, but 1 mole of oxygen is 16 grams of oxygen. This is 2 separate components. So as far as what I get for my mole values, 29.84 divided by that 22.99, I get 1.298 moles of sodium. Here I get 67.49 divided by the 51.996 gives us 1.298 moles of chromium. Ooh, I like that. I like how they're the same number, same ratio. 72.76 divided by 16 gives us an outlier 4.548 moles of oxygen. Okay, so we write our pseudo formula. So I've got sodium, and it's going to have 1.298, chromium, which is also going to have the 1.298, and oxygen, which is going to have this 4.548. So I divide by my smallest, which is this 1.298, and hope that we end up with all whole numbers. Well, I know anything divided by itself is 1, so I'm going to have 1 sodium. Chromium is also going to be 1. We've got to see what happens with that last number. So we take our 4.548 and divide it by the 1.298. And I end up with oxygen at 3.5. Okay. So this was what I wanted us to get to and see. So if after you've divided, you end up that you still don't have all whole numbers, you multiply this by some sort of factor to get rid of the whole numbers. So what is acting as my decimal still here is this 0.5. So going back to that reference chart, and it probably just like intuitively makes sense, 0.5, I would multiply by 2 to get rid of that. But if it doesn't make sense to you, then here is a chart with those values. So if you end up with a decimal of 0.5, you multiply by 2. If you end up with a decimal of 0.33, you multiply by 3. 0.25, a quarter, you multiply by 4. 0.2, multiply by 5. Even 0.1, you would multiply by 10. So you don't want to round things that are farther out than a tenth. So in this case, we're going to multiply everything by 2. And we don't just do it to the number that's giving us an issue. We have to multiply everything by 2. So this has to get multiplied by 2, this has to get multiplied by 2, and so does this. So my actual whole number ratio is going to be Na2, Cr2, O, and we take our 3.5 and multiply by 2, which will give us 7. So that's our lowest whole number ratio. Any questions on that last step, adding that last step in if you have to? So if you end up with something like a decimal that's 3.5 or 1.33, don't just say, oh, that's close enough to 1. It's not, we've got to multiply. So there's one other thing that I want to talk about in this section here, and that is the molecular formula and how the molecular formula relates. So if you know your empirical formula, let's say we're looking at, back to the previous slide. We'll look at this here. Okay. So I want to know what the molecular formula of fructose is. And I know, because let's say we solved for this in the previous problem, that we know the fructose formula is the empirical formula is CH2O. If I tell you that its molar mass, or how much it actually weighs in real space, like one molecule, if I tell you that it weighs 180.2 grams per mole, you should be able to figure out the molecular formula. How are you going to do that? Well, your molecular formula for fructose is going to be the empirical formula times N. And remember, N is that multiplier. It's a whole number. Is it twice as big? Is it 3 times as big? So what you need to do is calculate N and then feed it into this equation. Now, N here equals the molar mass, and this is the molecular. This will always be given to you, all right? Or you have to find it experimentally. Well, we're not going to be running any experiments in our houses. So this top value will be given to you. The bottom value you calculate from the empirical formula. So you're taking the mass of the molecular, the bigger guy, and dividing it by the mass of the empirical, or the smaller guy, to see how many times bigger the molecular is than the empirical. If this number is twice as big as this number, your N will equal 2, meaning your molecular is twice as big. If it's 6 times as big, N equals 6, okay? So molecular will be given to you. Empirical you solve by using the empirical formula. So let's go to that next problem. Or the problem that we were looking at on the next page. If I know that the molar mass, and when it says molar mass, it's talking about the molecular, all right? I know that the molar mass is 180. I want to figure out what my molecular formula is. Well, I need to figure out N. So N is going to equal molecular over empirical. My molecular is given. Okay, so we know that the molecular is 180.2 grams per mole. The empirical I have to calculate. So I have to look at the formula and add all those things together. So I take the mass of a carbon, which is 12.01. And I have to add it to 2 hydrogens. 2 hydrogens with 2.02 would be the mass. And then I need to throw in an oxygen, 16. So my overall mass for my empirical formula is 30.03. So I take the 180 and I divide it by 30. And what we get is an N value equal to 6. Or my molecular formula is 6 times as big as my empirical formula. Now, am I done? Not yet. I have to thread it back in to see what my molecular formula is. So molecular formula is going to equal that empirical formula, which is the CH2O, times what my N value was, which was 6. So if I multiply each of these things by my value of 6, I should get C6H12O6. This is what's actually happening. We have 6 carbons combined with 12 hydrogens and 6 oxygens. All right, so you solve for your N and you multiply it by your empirical. Now, N will always be a whole number. So if you happen to mess it up and flip these two and you're getting a decimal, you've done it incorrectly. So just make sure the bigger number sits on top so you get a whole number. So let's do an example of this off of a problem you guys already worked on. So we were at, where was it? Here we go. Okay, so let's go back to this first problem and we'll do number 2. So you have the formula for 1. I don't remember what it was. C3H3O. Okay. So we've got that this is C3H3O because you already figured that out. I want you to do number 2. So if the molar mass of the compound is 110, what is the molecular formula? So you've got the molecular mass, solve your empirical mass, see how much bigger it is, and then multiply it out. I'll give you 3 minutes to do that. That part is a little bit easier, I think, than the first one. Okay, so back together as a group. So we've got C3H3O, and usually this is something that you are either going to be given if it's just testing you on this part, or you would have like already solved it. So this is our empirical. I've got a molar mass. Molar mass is always going to be talking about the molecular when it's given. Okay, now I want to find the molecular formula. So my molecular formula is going to be C3H3O times a value N. Now, in order to find my value N, I need to figure out how much bigger the molecular molecule is than the empirical formula. So N is equal to molecular over empirical. Remember, molecular is given, empirical you calculate. So my molecular was 110 grams per mole. My empirical, I don't know, let me calculate it here, 2 seconds, is 12.01 times 3 plus 3.03 plus oxygen 16. All right, so we got 55 or 55.06, somewhere around there, grams per mole. So I take my 110 and divide it by 55, and we get a value of 2. So I'm going to plug 2 into this thing right here because my molecular formula is going to be twice as big as my empirical. So if I put 2 here, the 2 gets distributed out to each one of those values. All right, so we've got C6, H6, O2. There is the molecular off of the empirical. Any questions on that process? We'll do one more just for fun. So we had that lithium carbonate problem. If you have questions, pop it in there. So let's do number 4 here. 4 is talking about that problem 3 that you did. So we had lithium carbonate. And if we know that the mass is 73.8, what is the molecular formula? So we got lithium carbonate, CO3, Li2CO3. All right, so I'll give you 3 minutes for that. Okay, so for this one, you may be wondering, is it the same? It is the same. Sometimes the empirical and the molecular formula are actually the same. There is no like multiplier. So we want to figure out molecular formula. So in this case, the molecular formula should equal my empirical, which is Li2, CO3 times some value n. The value n, remember, is going to equal my molecular over my empirical mass. Molecular is given, empirical is something you calculate. So there's my molecular, it's 73.8 grams per mole. My empirical formula or empirical mass, I have to calculate. So I take the mass of 2 lithiums, I add it to 1 carbon and 3 oxygens. And what do you know? You end up getting 73.8 grams per mole. So what happens is your n value is equal to 1. So your molecular formula is 1 times as big, or one times as big. It's the same value, right? So if I plug 1 in here, I'm going to end up with Li2CO3. Can that happen? Totally can happen. A lot of times with our ionic stuff or our metal nonmetals or our salts, the molecular and empirical will be the same. Okay, so any questions on those, on being able to solve those? You'll definitely have a problem like that on there. Hopefully that felt, we did enough of them that felt easy. If you're having trouble with it, you can always go back through the videos and rewatch it. I do recommend those worksheets. Those are really helpful if you want something to practice on them. So that's the end of chapter, it's the end of chapter 6. It's like the chapter that keeps on giving. I think it's the longest chapter in the whole semester. But we're gonna start just peeking at chapter 7 so that we can have cushion time next week. We are ahead already, but let's just do it. Oh, why don't I have a label there? That bothers me. Okay, I'm gonna change that at some point. Chemical reactions. So this whole, no, I don't want that. Unless it's not going to let me open it when everything is. There we go. All right, so the next chapter, the first chapter was talking all about quantities. This next chapter is talking about all about chemical reactions. So when we mix things together, not mix, but when we react things together, what are our products, how to predict chemical reactions, how to label chemical reactions, how to balance chemical reactions. And then the following chapter after this combines numbers and balancing equations together in stoichiometry. So evidence of a chemical reaction, if you've ever done this experiment where you take in vinegar and baking soda and you made like a volcano, it has this effervescent quality to it, or it fizzes. And that's because you're converting the acetic acid in the vinegar and the sodium bicarbonate in the baking soda. You're turning in a carbon dioxide gas and water. So the carbon dioxide gas is what's making it appear kind of fizzy. The new formed bubbles are a good indicator that a reaction has occurred. Anytime a liquid, a gas, or a solid form, when those weren't initially there, like we had here, we had a liquid and a solid, and all of a sudden a gas formed, that's a good indicator that a chemical reaction has occurred. Here's another example of a chemical reaction. This is specifically a type of reaction called a combustion reaction, and I'll talk to you a little bit later about how to identify those. But this is what's going on in your car. So we take octane, which is one of the main components in gasoline. Gasoline is a mixture of a couple different things, but octane meaning that it's a chain of carbons with 8 carbons. Specifically, that's why it's called octane. We combust it with oxygen. So in order to combust something, you need to combine it with oxygen. A great example of this is when you are, when you're burning wood for a fire, you blow on the fire to give it oxygen so that it'll combust better. Same thing with your car. If you've got like a filter that isn't cleaned properly and it's not getting oxygen into the engine, this combustion will not run as efficiently. So we need this, we combine it with oxygen, it runs through our engine and it produces a bunch of heat. That's the energy that we capture to run the car. And then outside of your tailpipe, you produce CO2 and water vapor. Okay, so water vapor, relatively harmless. CO2 and low concentrations also relatively harmless, but a lot of us run our cars all the time, constantly. So we do have an increase in this thing here, which is a greenhouse gas. Combustion reactions are a subcategory, and again, we'll get into this, of oxidation reduction reactions. This is where we transfer electrons. And we'll talk more about that later. Laundry detergent, okay, another type of chemical reaction. So evidence of a chemical reaction. How do you know a chemical reaction has occurred? Well, if we could see the atoms and molecules that compose matter, it would be really easy for us to determine if it was a chemical reaction, because what would happen is atoms would switch partners, they would move around, they would form new molecules, or they decompose from the original molecules. We'd have this sort of dancing around of the atoms. That would be really easy if we could see it, but with our eyes, we can't see these atoms exchanging places or moving around. So we have to look at secondary evidence to tell us that a chemical reaction has occurred. What are some of those secondary things? One is color change, but color change is tricky because it's not always evidence of a chemical reaction. Sometimes when things phase change, go from a solid to a liquid or a liquid to a gas, they can actually change color as well. So sometimes color change. These other things, though, are definitely a good indicator. The formation of a solid, or sometimes this is called a precipitate. So we had two liquids, and then all of a sudden we get this like clunky, cloudy solid forming at the bottom. That's a good indicator that a chemical reaction has occurred. The formation of gas, so this is one of those little Alka-Seltzers, what it is. You drop it in and it fizzes the water. That's a good indicator anytime you have a formation of gas from two things that were not initially a gas. Emission of light. So this little glow stick here, you break the glow stick and the two chemicals mix together and it emits light. And then also anytime you are giving off heat or absorbing heat, that's a nice indicator that a chemical reaction has occurred. So here's another indication of a precipitate reaction. We had a yellow material, which I'm guessing was some sort of like iron oxide, just based off of its color. And then we have a liquid here. When we dropped this in, we've got this sort of cloudy red color solid that's starting to collect at the bottom. Here we've got a gas formation. Certain things that are not evidence of a chemical reaction, okay? Boiling water is not an example of a chemical reaction. And it may look like a chemical reaction because you're saying, well, look at all the bubbles. Didn't we say that bubbles forming was a chemical reaction? Not if you're applying heat, all right? If you're applying heat here, all you're doing is changing this thing's phase. You're not actually changing what it is on an atomic level. So if we look at this coffee pot here, we've got liquid water in the bottom. We have gaseous H2O coming out. They're still H2O molecules. These just happen to be in liquid form. These happen to be in gaseous form. I haven't changed into new atoms. I have to become something new in order for it to be a chemical reaction. Only a chemical analysis where we figure out what we started with and what we ended with will tell us that there's actually been a chemical change. So there you go. So how do we write that a chemical reaction has happened? Like we're really good, hopefully now with writing chemical formulas, so you know your little recipes for your compounds. Now we're gonna take these formulas and we're gonna combine them together to form a chemical equation. So in a chemical equation, this is how it's always gonna be set up. On the left side, you're going to have your reactants. How many reactants can you have? You have to have a minimum of one. And then that can go up to hundreds. Each reactant that you add will be separated by a plus sign. Then you're going to have your products on the right side. So just like you would read a book from left to right, you'll read your reactant or your reaction from left to right. The products will be on the right side. You can have, well, you have to have a minimum of one, but you can have a bunch of them after that. And then again, they'll be separated by a plus symbol. We like to add the state when we can. So saying, hey, iron is combining with oxygen, but not just iron, solid iron is combining with gaseous oxygen. And then those are separated by an arrow. Okay, so there's the symbols, gas for G for gas, L for liquid, S for solid. And then there's this thing here, AQ. That's aqueous. And we're going to see that a lot, especially when we get into the solutions chapters. later on in the acid-base chapters, because sometimes it doesn't make sense to present something in its like pure form. We want to dissolve it in water and then present it as a solution. So if it's being presented to the system as a solution, we'd write it as aqueous. So let's say I had a hunk of salt, NaCl. If it was just a hunk in solid form, I'd write it as S. But if I didn't want to present it as a solid, I could dissolve the salt in water and I would present it in an aqueous solution then. Okay, so know that this and this are the same material, but they're being presented differently. One's a solid, one's dissolved. All right, so here's an equation. This is a combustion reaction, specifically combustion of methane. Methane is a very simple hydrocarbon, just one carbon. You are not going to be naming organics, so I wouldn't expect you to know that this is methane. I wouldn't expect you to know what the formula for octane is. But you do have to be able to identify that this is like a hydrocarbon, hydrogen, and carbon. So here are my reactants. I've got carbon, I've got methane. I'm adding it to oxygen. So these are two reactants separated by a plus. My arrow says that some sort of change has occurred. So I'm no longer going to end with these two things. Instead, I end up with CO2 and H2O as my products. If I fill in with my phases, I would say methane gaseous is added to oxygen gaseous to produce gaseous CO2 and gaseous H2O. Now, like I wouldn't expect you to know that methane is a gas, but I do want you to know that oxygen is a gas. I do want you to know that water is a liquid, like some of the like basic ones. You should be good with here. This is water is a gas, so I guess that would throw you off. Really, don't let the phases trick you. I will give you the phases, but oxygen is one I do want you to know is a gas. Okay, so looking at this is a chemical reaction, but it's not correct because it's not balanced. And what I mean by balanced is, let's look at what's happening here. If I add up, let's say the oxygens, I have two oxygens on the left side, or my starting side. I have two oxygens in the CO2 on the product side and one oxygen in the water. So over here, I have a total of 3 oxygens. So I started with 2 oxygens and all of a sudden I have 3 oxygens. That is not possible, okay? In a chemical reaction, you cannot just create matter. Remember, the law of conservation of mass says that in a chemical reaction, matter is not created nor destroyed. So what I have on my starting side, atom-wise, I need to have on my ending side. Those two numbers need to equal each other. If they don't, you have an unbalanced equation. There's also something wrong with my hydrogens. Over here, I have 4 hydrogens. Over here, I have 2 hydrogens. So what you're telling me is that 2 of these hydrogens just sort of disappeared. You know, you shove them under the universal rug somewhere and we can't find them. That's not going to work. Okay, so we have to balance this thing. So when I balance this, what I could say is that for every 1 methane, I'm going to take 2. I put a 2 in front of the O2. I'm going to take 2 of these diatomic molecules and it will yield 1 CO2 and 2 waters. Now that will balance out the number of oxygens. Here I have 4 oxygens. Here I have 1, 2, 3, 4 oxygens. Here I've got 4 hydrogens. Here I now have 4 hydrogens. I have 1 carbon and 1 carbon. So those are all balanced. We like that. When you're balancing equations, you only change or adjust coefficients. So we just play around with numbers that sit in front of your compounds. We never change subscripts. I would never want to change this number or change this number. Why? Because then you would have a different material. What I see happen sometimes is people will say, oh, well, I have 4 hydrogens here, so I need 4 hydrogens over here. So why don't I just change this to H4O? Well, is that water? No, that's definitely not water. So we don't want to be doing that. So we're just going to be changing coefficients. There's a set of rules on how you change and why you change and the ordering that you change. And we will get into that next time since it's 9:15. So we're done today. We will continue on with this on Wednesday. Let me know if you have any questions. Good work today. Enjoy the rest of your afternoon. If you haven't voted, go vote. Otherwise, I will see you guys soon. Bye.